So we are talking about the method of partial fractions. So can anybody roughly tell me what happens? Maybe your brains have been erased by the exam in the meantime. So if you don't remember, that's okay. Anybody, what do we use them for? So we've got this method of partial fractions. It's used to integrate some kinds of functions, right? What kind of functions? Rational functions, right? So use on rational functions, proper rational functions. And if I gave you something like x squared plus 5x plus 2 over x plus 1 squared x squared plus 1, then you could tell me you were sort of told, although like I said last time, we didn't explain it and we're not going to explain it, that this thing could be expressed as a sum of partial fractions, right? So what would in this case, what would the partial fractions look like? Right, we've got this linear term squared, so we're going to have, anybody remember, what are we going to have over here? Got this linear term squared, so you're going to have some guys over here. Right, Elizabeth?
Is it like a over quantity x plus 1 and then maybe like b over quantity x plus 1 squared?
Great. Right. So you'll have things, some constant over the linear term to the first power, some constant over the linear term to the second power, right? And then we've got this quadratic term, this irreducible quadratic, right? It's got no real roots. Got this irreducible quadratic, and so you know that there's going to be something over here. It's to the first power, so you know that you can have something involving the quadratic to the first power only, and on the top you're going to have some linear. You're going to have some linear term, right? So cx plus d, right? So you have some term of a lower degree, right? If it's a linear term on the bottom, a degree 1 term, then you have a degree 0 term here, right? I should say, yeah. So if you have linear terms, then you have constants on the top, right? If you have quadratic terms, you have these linear terms on the top. Okay. So that's where we stopped, right? We stopped showing you that, if you have something like this, then its form is going to be like this. And the question that you had at that point was, how do you figure out what A, B, C, and D are, right? So that's the question. How to determine the constants. Okay, so there are a couple of methods. The first is based on the identity theorem. Use the identity theorem, and remember what the identity theorem said that equal polynomials must have identical constants, identical coefficients. Equal polynomials must have identical coefficients, right? You can't have two polynomials that agree and have different coefficients, right? In fact, we saw that you can't have two polynomials that even agree in a tiny interval and have different constants, which is kind of remarkable. Okay, so let's give an example. So the simple example, 1 over x plus 2, x minus 2, right? So, somebody starts you off with 1 over x squared minus 4, and you say, oh, look, this thing I can break into linear terms, right? I can factor this into x plus 2, x minus 2. I don't leave it as x squared minus 4, right? Because that's a reducible quadratic, right? this guy was irreducible, but this guy is reducible. Okay, so you would factor it, and you say, okay, I've got these linear terms, and so I know it's going to be some constant over x plus 2 plus some constant over x minus 2. Okay. And then you multiply through by x. So multiply both sides by x plus 2 times x minus 2. Okay. And you would get 1 equals a times x minus 2 plus b times x plus 2. Okay, so right, multiply the left by x plus 2 times x minus 2, you get 1. Multiply the right, you get a times x minus 2 plus b times x plus 2. Right? Everybody okay? Any questions? Okay, so, and now you use the identity theorem. You say, well, I've got a polynomial on the right-hand side, and I've got a polynomial on the left-hand side. Right? Right? On the right-hand side, I've got ax plus, sorry, let me do it like this. I got a plus b x minus 2a plus 2b. Right? If I multiply this out, group the terms with x's, right? Ax plus bx, right? I've got a plus bx. I've got negative 2a. I've got positive 2b, right? And on the left-hand side, I have 1, right? So, to make it more clear, I've got 0x plus 1. Right? I've got this polynomial on the left-hand side, 0x plus 1. On the right-hand side, I also have a polynomial, a plus bx minus 2a plus 2b. Okay? And then you say, okay, well, the left-hand side agrees with the right-hand side everywhere, right? For all x, they agree. So that means that these are the same polynomial, and so the coefficients must be the same. So by the identity theorem, you know that 0 must be a plus b. You know that 1 must be negative 2a plus 2b. Okay. You return to junior high school, right? You solve your simultaneous equations, right? You say, okay, you do however you want to do it. You make it substitute. You can say, I'm going to take a is negative b, right? A equals negative, I don't know. You know how to do this, right? A equals negative b, so I get 4b equals 1, right? A equals negative b, substitute that in here, right? You get that 4b is equal to 1, so 4b equals 1, and so b is a quarter, and a being negative b is negative a quarter. Right, however you want to do it. Okay, so right, so you get the identity theorem give you these two equations, and then you solve them, and you figure out what a and b are, and that's it, right? So you know that a is negative a quarter, and b is a positive quarter, right? So come back here, and you know that this is negative a fourth over x plus 2 plus a fourth over x minus 2. Okay, and so that gives you your partial fraction decomposition. Okay, you figured out the coefficients in the partial fraction decomposition. Okay, everybody okay? Right. So, right. Start with your partial fraction decomposition. Multiply through. Clear out the denominator. Right. Clear out the denominator, and then realize that the coefficients must be the same on both sides. And that's all. Yes, sir.
So always equal 1. When you get the when you go from when you're multiplying both sides out, you always get 1.
No, right. If we had something else on the top here, we would get that whatever that was.
Oh, I see.
Right.
Okay.
We get 1 because we multiplied through and we got 1 here. Yeah. Yeah. So no, not necessarily. Okay. Okay. So method 2, we'll do the same example. So evaluate at various points. Okay. So maybe I should say cleverly chosen points. Cleverly chosen points. So again, you have this thing. 1 over x plus 2x minus 2 equals a over x minus 2 plus b over x plus 2, right? And you multiply through, and you get 1 equals a x plus 2 plus b x minus 2. Okay, and you know this is true. This is true for all x. Right? You know this is true for all x. And so what you do is you say, well, I'm going to evaluate at x equals minus 2. Say. Okay, and so I would get 1 equals 0a minus 4b, right? You get 1 equals negative 4b. Right? Just let x equal negative 2. This term is going to vanish, right? I chose the negative 2 so that this would vanish. And then I get negative 4b is equal to 1. And so b is negative a quarter. Okay. And you also could evaluate, you know, the other obvious choice for x is 2, right? So you plug in x equals 2, this term vanishes, and you get 4a equals 1, and so you get a equals a quarter. Okay, so it's method number 2. Method number 3 is actually almost the same thing as method number 1, but maybe looks a little different. Method 3, evaluate the derivatives at cleverly chosen points. Okay, so right, you have a equals, I'm sorry, 1 equals a x plus 2 plus b x minus 2. Okay, and then you could differentiate both signs. Differentiate. And you get 0 equals a plus b. Right? And then maybe you evaluate the original one at x equals 2. Right? And you get 1 equals 4a. Right? Okay, and so you get, you know, a equals a quarter, and a equals negative b, so b is negative a quarter. Okay, and you notice that this is in fact exactly, it's equivalent to the first method. because when you differentiate, you're picking off the coefficients on the x term. Right, you get rid of the constants and just get the coefficients on the first term, on the x to the 1 term. But that's what we did in the first method. And we looked at the coefficients on the x to the 1 term, and that's them, right? 0 on the left side, a plus b on the right side. So it's actually no different. Okay, any questions on how to find the coefficients? Let's do any questions? Right, pretty straightforward. Either use the identity, or evaluate, or take derivatives and evaluate, or do some combination. Okay. Right, and then once you're done, then sorry, I should have said this. Oops. We ended up with 1/4 x plus 2 negative a quarter x minus x plus 2. 1/4 over x minus 2 plus negative a quarter over x plus 2, right? And so then you go back to your original problem, right? Your original problem was to integrate this, right? The original problem was to integrate this, and you say, okay, well, all I have to do is integrate this, and this is easy to integrate, right? Because you've got, how do you integrate 1 over x? It's the natural log, right? So it's going to be a quarter of the natural log of the absolute value of x minus 2 minus a quarter of the natural log of the absolute value of x plus 2, right? So you end up with 1/4 natural log x minus 2 minus a quarter natural log x plus 2. Which is not completely obvious from looking at, if you just look at this, it's not completely obvious that that's the answer, right? Without doing it this way, maybe you'd use some trigonometric substitution. Okay, let me have you try a slightly more complicated one. So instead of having 1 on the top this time, we're going to have 2x squared plus 3. On the bottom, we have x minus 1 squared. Okay. And, okay, so figure out what the partial fraction decomposition is. Okay. Take 2 minutes or 3 minutes and see if you can do it. Okay, turn to somebody nearby and tell them how you did it.
I did the you give the okay.
One is quarter, so you get 1/4, and then you put it in here. Also, you use this code to evaluate the variable. Yeah.
Okay. Somebody want to tell me just the form of it? What is the form?
A by x
A over x.
plus b over x minus 1
Mhm.
plus c over x minus 1 squared.
Yes. Okay. And then you multiply through, right? You get 2x squared plus 3 equals a x minus 1 squared plus b x minus 1 plus c. Right.
Wait, would it be CX?
Ah, cx, excuse me. X.
Used to writing plus C and doing it.
Yeah, that's the trouble. Okay, yeah, plus cx. Okay, so then you multiply things out and you get that. I don't know. Well, how did people do it? Anybody want to choose a method? First method, second method, third method? First. Okay. Okay, so you multiply things out, right? You get, I think, a plus b x squared plus negative 2a minus b plus c x, and then plus a. I hope. Is that what people got? Right. You get 2x squared plus 3 equals this. Right. But, okay, so you say, okay, so then you get a plus b equals 2, negative 2a minus b plus c equals 0, and you get a equals 3. Right? Okay, and then you work it out. You see that a is 3, so b is negative 1, right? Put these two guys together, give you that b is negative 1, and then you put that in here, right? And you see that c equals 5. Right. Negative 6. Yeah. Negative 5 plus c equals 0, so c equals 5. Yes, Marie?
Sorry, why is it bx x minus 1 as opposed to just...
Because we multiply both sides by the denominator here.
Okay.
So you say, okay, we're going to multiply everything by this, right? On this side also, you multiply everything by x minus 1 squared, right? And so the x's, for this guy, the x's will cancel and you get x minus 1 squared.
Okay.
Right, for this guy, one of the x minus 1s will cancel, but you have one left over. So you get x minus 1. And you have this b over x minus 1 times x minus 1 squared. Well, one of them will cancel out, but you've got one left over. Right? And then the last one will be x minus 1 squares cancel out, and you get the x left over. Okay, so pretty easy, right? So you figured out what it is. A is 3, B is -1, and C equals 5. Okay, and then you can integrate that pretty easily. Okay, notice that we could have done some combination of things, right? Like you start off, you know that A is 3. With this, you get that B is equal to -1. And if you wanted C, well, if you're lazy and wanted C, you'd say, okay, I'm going to let x equal 1. Right? I'm going to take x equal 1 here. I get 5 equals 0 plus 0 plus C. Right? C is equal to 5. Right? So you could substitute. You could substitute. Just evaluate this guy at x equals 1, and you get 5 equals C immediately. Okay. If you felt like it, but it doesn't. It's not hard either way. Mira.
How did you know that A was 3?
A was 3 because from here, right, we worked out all the coefficients, right? We worked out all the coefficients. We see that the coefficient of x squared is a plus b. So a plus b and 2 must be the same, right? The coefficient of x over here is 0, right? Because 0x plus 3, right? So we see that this thing equals 0. And then the coefficient of 1 is 3. Right? We've secretly made an x to the 0. Right? X to the 0. Right? The coefficient of x to the 0 is 3, and the coefficient of x to the 0 is a. Okay. Just one more. Seems like it's pretty easy for you. Just to make sure, let me give you another one. X squared plus 5x plus 2 over x plus 1, x squared plus 1. Okay, turn to somebody nearby and talk with them, please.
But, wouldn't it be BX plus C it's supposed to be like if it's quadratic, it's supposed to be CX plus D. Yeah, I mean, I still haven't figured it out, but like how I initially wrote it out was like this, and then I'm trying to figure it out, but it's obviously harder.
So I was trying to watch
Okay, so what did people get for the coefficients? Does somebody want to say what they got? -1, 2, 3. Yeah, that's right. At least that's what I got. I think that's right. Okay. Now that we think we know what the coefficients are, does somebody want to say how they got them? No? Oh, I see you're answering. Yeah, Jessica, go ahead.
I did A over X plus 1 plus BX plus C over X squared plus 1.
Sure. Right. You can't factor this any further, right? So you say, okay, I'm going to have this quadratic, irreducible quadratic, and I'm going to have a linear term on top, right? And then you multiply through, then x squared plus 5x plus 2 equals a x squared plus 1 plus bx plus c x plus 1. Right? And what do you do from there?
And then I just like multiplied the right side out, and I got A plus B X squared plus B plus C parentheses X plus A plus C.
Okay.
And then A plus B equals 1, B plus C equals 5, and then A plus C equals 2. And then I evaluated at X equals -1,
Okay.
and then I got 2A equals -2.
2a equals -2. Yeah, that's a good thing, right? Because x equals -1 kills off this whole thing here, right? And so you get 2a, 2a equals -2, and so a is -1, right? And then you plugged in things, and then you figured out what b and c were, right? Right. C is going to be 3, and then b has to be 2. Okay. Yes, Kara.
Where did you get the -2 from? Or like 2?
This guy? So it's so she evaluated this thing she evaluated this equation here at x equals -1, right? Which is good because that will kill off this whole thing, right? This whole thing will become 0, right? Because you'll get, when x is -1, this becomes 0, right? And you end up with a times 2, right? And then you're going to get 1, 3, minus 5, -2 on the left-hand side. So you get a -2 equals 2a plus 0. Right? So yeah, So, yeah, I mean, there was enough, certainly there's enough information here to figure it out. Right? You've got 3 equations, you've got 3 unknowns, you know, back in junior high school, you can do it. Right? But, you know, why not make use of this little bit of extra information by evaluating at a pretty convenient point, right? That tells you immediately what A is. Right? So. Other questions? Everybody think you understand how to do it? So then once we have that, we say, okay, well then the integral right? So if I gave you this integral 2 days ago and I said, integrate this, right? It'd be pretty hard. But now you say, okay, I use the method of partial fraction decomposition, and this is going to be, what are my constants? -1 over x plus 1 plus 2x plus 3 over x squared plus 1 dx. Right? And so you integrate this first part. What's the integral of the first part? Obviously, right, it's easy. Negative natural log absolute value x plus 1, right? And then we integrate this guy. How would you integrate this guy? A couple ways you could do it, but how would you? Maybe if you wanted to use the logarithm again, you'd say, well, I want to have 2x. It's good that I've got this 2x on the top, right? But I've got this 3. So I'm just going to ignore the 3. Right? And I'll move it over somewhere else. Okay? Right? Why not? You can do that. Right? Okay. So then this thing here turns into natural log of absolute value of x squared plus 1. I guess I can get rid of the absolute values since x squared is always positive. Right? And then you've got this 3 over x squared plus 1. We've seen this x squared plus 1 before. 1 over x squared plus 1's antiderivative. We worked this out a couple of days ago. Does anybody remember? It is the, not the tangent, but the arctangent. Yes, exactly. So you get plus 3 arctangent x plus a constant. Okay. So, right, this seemingly difficult integral, use method of partial fraction decomposition. It's pretty easy. This C is not the same C. Sorry. I should probably use C prime. I use curly C. Okay. Okay, that's it for today. I don't want to get into the next section with only 4 minutes left. So let's stop here and see you next time.